Welcome to ECEN 215 Principles of Electrical Engineering. This is one of 3 lectures on nodal circuit analysis. This first one of 3 is just an introduction on the concept and working out one general problem just to kind of show the base concept. There are 2 more lectures, one covering how to solve a set of linear equations using linear algebra, which is not a requirement for this class, but is a helpful way of using mathematical technique for solving a set of linear equations that we're going to be developing with these circuit analysis methods. So let's just go ahead and get started on this. So first, we're going to again talk about the basis for node voltage circuit analysis, which is Kirchhoff's current law. And this is, again, from the very first set of slides we had earlier in the class, I believe lecture 2. And this is just simply stating that the net current entering a node is 0. And a node is any place where 2 circuit elements join together. So literally, this is the same slide. You've seen this before. We have 3 different circuits here, or sub-circuits, and we have, in the case of circuit A here, we have 3 elements. Circuit B, we have 2, and circuit C, we have 3. And notice we have node A, node B, and node C. And it's just where the 3 circuit elements come together. And we've labeled our currents, that was when we were talking about current and voltages the other day. We have an arrow, and we have simply that the current is flowing in the direction of the arrow. So if the current here was 5 amps, that means 5 amps is flowing this direction. And if the current is minus 5 amps, using this convention, that means the current is actually flowing in that direction. So it's just important that you understand, again, the purpose of the arrow, and it also, when we talk about circuit elements where we assign pluses and minuses, that for an absorbing circuit, again, if the current is flowing from the positive to the negative, it's absorbing. So we have 5 amps flowing through it in this direction. Then we would expect to have a voltage drop of, say, 5 volts across this. And using Ohm's law, if this was a resistor, say, and we had 5 volts across this element and 5 amps, then corresponding the resistance would be equal to 5 volts divided by 5 amps, which would be equal to 1 ohms. So just to make sure you understand the principles here, because we're going to be building upon this. So we have 3 circuits here, and we have simply I1, I2, and I3. And since in the node itself, we cannot have any holding of current. The node does not store current. It is just a connection point. That correspondingly means that we can write a set of equations. And so we write that I1 minus I2 plus I3 is equal to 0. And what this, and you're going to hear me say this over and over again, it's you either choose entering as positive or negative. You choose what it means. In this, I always use leaving a node. It's always very easy to do that. So if we have I3 is positive, and then therefore I1 and I2 must be negative. So since I have arbitrarily said when I'm writing this equation that I3 needs to be positive, in other words, all current leaving the node will make positive, all current entering the node would be negative, then we can simply write minus I1 because it's entering the node, I2 again because it's entering the node, plus I3 since it's leaving the node must be equal to 0. And that's just simply using the fact that the net current entering the node must be to 0. And so correspondingly, we have the same thing for node B here. We have minus I3 because we're entering the node for node B, but we're leaving for I4. So it's simply, the equation is minus I3 plus I4. And then, of course, for node C, it's the same thing, minus I5, minus I7, and then minus I6. Correspondingly, we simplify this. We simply get I3 is equal to I1 plus I2, I4 is equal to I3, and I5 is equal to minus I6 plus a negative I7 or minus I7. So again, this is just a review from the lecture we had the other day. Correspondingly here, we have three elements in series. Well, IA is equal to IB plus IC. So if you write an equation for node 1 and node 2, you would correspondingly get the same thing because there's no place where the current can't go. So these are all equal. It's all one current going through the circuit. So now we have that. Here's just one more slide of review. This is again from lecture number 2, and it's just showing how we have these different nodes. We have node 1 and we have node 2. We write a set of equations based upon currents. Now, how do we get current? So if I use Ohm's law, I can get current. If I know the voltage across an element, I get current. So in this case, we have IC, right? So let's just say arbitrarily, I define this as plus and minus like this, because the currents go in this direction. I want to call this VC. Okay, what is VC? So VC is equal to IC, and we're just going to assume these for the moment are resistors. So this is RC. RC, right? Well, correspondingly, we know IC is equal to VC over RC. So we can solve for IC in terms of the voltages of the elements. And we're going to use this in nodal voltage circuit analysis. So again, let's do element A. Let's pretend this is a resistor, and we're going to give it resistance RA. And then we're going to call it this plus and this minus. Again, using the direction of arrow as our guide here. Then IA is equal to VA, and VA being defined as this positive and this negative over RA. So it's very important that you make sure that the arrows and the plus and minuses agree. Else you're going to get things backwards and your math is not going to balance. So just real quick, I'm just going to erase this. We'll do one more just so that you can see the principle before we actually go through the steps of nodal circuit analysis. I'd probably say in most of the questions that I get on these methods where people seem to get tricked, if you will, or tripped up on the problem, it's just simply they're not following convention or direction. So again, let's just look at element B. So we'll set the direction following the arrow. Again, we're assuming everything here are resistors, so RB. So IB, and being a resistor, it goes in the direction of the arrow. Since this is an absorbing device, that means the current entering the positive terminal to negative terminal causes a voltage from positive to negative. So that's what we're doing here. So again, IB is equal to VB over RB. Okay, so now let's actually talk about what are the steps for doing nodal circuit analysis. So before I jump in, why do we do circuit analysis? Well, we have a circuit and we have all these different current and voltages, and these could be, and granted the problems that we have in this class are very straightforward and just mostly that you're going to see just a bunch of resistors and maybe some power supplies. But in real world applications, you're going to have multiple supplies. You're going to have and we're going to learn this later in the class, operational amplifiers. You're going to have different input signals from like pressure transducers. You could have level sensors that output a current or a voltage or change their resistance based upon the pressure. That's really common. Actually, it's called a strain gauge interface, where as the pressure in a vessel increases and you've got a sensor that's exposed to that pressure, its resistance will increase and decrease depending on the pressure. So if the pressure is at, say, 0 psig, it could be 1,000 ohms. But as the pressure increases, it has a linear relationship, so that if it goes to 1,000 psi, instead of 1,000 ohms, it's now 10,000 ohms. And so you're going to want to measure the voltage drop across that resistive element, the sensor, and you're going to want to amplify that value and have a linear relationship that you can track with the computer and then put on the screen instead of putting ohms, you'll have an equation that gives you 0 psig, 1000 psig, and anything in between. So that's what we're going for here. So you're going to do a circuit analysis to end up deriving values that you will use to display for certain parameters in an industrial application. That's just an example of where this is used. So moving on, let's start with nodal voltage circuit analysis. So the very first step of this process, and there are a total of 5 total steps. So step 1 is we have a circuit and we've got to create a reference node. So here we have this circuit, and this circuit is very similar to ones we've seen in the past. We have 5 resistors, we have a power supply Vs, and we've created this reference node here. We call it a ground symbol just to denote 0. It is simply node 0. That every voltage that we're going to declare, every node voltage will be reference to 0, reference to this reference node, this ground node. So we sometimes label it actually as net 0 to represent that. So that is the reference node. So as we learned the other day, when we call out, say we have a resistor and we labeled one side A and one side B, and you could declare voltage AB, meaning the drop across from VA to B. Here you're going to have something where you have an element, let's just call this R6 here, and we're going to have our reference node 0, right? And I'm going to have this we'll just call it V6. Then it's really V6 0, if you will. It's the voltage that's across here to here. So the same way, let's just use, before we actually dive in on the circuit here, if I've got 2 resistors in series, and I've got 2 nodes, call this A, B, and the ground, we have our ground node here, then voltage A is actually the voltage, and we'll just, for purposes of argument, we're going to call this G for ground. Then really when I give a voltage VA, it is actually VAG. It is the voltage from here to here. And voltage B at node B would be equal to VBG. It's the voltage from here to here, whereas the other one is this voltage. So it is the nodal voltage to ground, to the reference node, not across the element, but to the reference. So here we have 1, 2, 3, 4 total nodes in this problem. And so we've created this reference node. So that's the very first step. The next step is to assign the names of the nodes, to actually assign the node voltages. So again, I said we have a total of 4 nodes. One of them is the reference node. And then we have other nodes. We have node 1, 2, and 3. Sometimes we call this reference node node 0. So that's where you start at 0 and then you got 1, 2, and 3. And they don't have to be, you could call this node 1, you could rename this 1, you could call this 3, you could call this 2. It doesn't matter. It is up to you in the analysis as long as you're consistent and always use the same nomenclature all the way through the analysis. So in this example here, we have our reference node. We have node 1, which is where these 3 elements here are connected together. We have that. We have node 2, which is where this one, and this one are connected together. And then we have where these 3 elements are connected together. Right there. So we got 3 nodes. So that's step 2. Fairly straightforward so far. Nothing too complicated. So every place that you have a combined set of elements coming together is a node. So we have that. So very next step, 3, is we need to find the element voltages. So let's do that in terms of the node voltages. So here's our circuit, and we've all gone ahead and assigned the different elements. So we have VZ, VY, VX, and then of course V2 is just simply this one here, if you will, the one across R4. So we've added some additional, labels here. So we have VZ is the difference between 3 minus 1, right? That's the voltage drop across R1, is that one. We have VY is V2 minus V1, in other words, it's the voltage drop across this resistor. Vx, which is the voltage drop across R3, is simply V2 minus V3. And then the voltage drop across R4 and R5 are simplest enough, and they're just V2 and then V3 correspondingly. So we went ahead and wrote our equations that. Now also, what else do we know about this problem? What is V1? Do we know what V1 is? We are given, if this was an actual circuit analysis, we would be given what Vs is. This could be, for purposes of argument, this could be 12 volts DC. So you're given Vs. So this is a known. So what is Vs? Vs is simply equal to V1 because that is the node and it's an ideal power supply, and that ideal power supply is going to maintain the voltage with reference to its node voltage of its reference node here to V1. So no matter what's assigned here, if this is 20 volts, V1 is always 20 volts. It doesn't matter what else is connected to this. So now that we know that, we are going to come back and now write the KCL equations. So what that means, we're now going to take and work out a set of equations given all of these current and voltages, and we're going to want to do that in terms of V1, V2, and V3, and in terms of our node voltages. So here's our circuit, and we have VZ, we have VX, and VY, which we obviously also know in terms of V1, V2, V3. So when I usually do this, I don't usually do step 3. I sort of kind of skip through it because I instinctively already know that the voltage across R1 is V3 minus V1. But it's a good thing until you get into that practice of knowing the voltage drop across R1 is V3 minus V1 that you probably write that. But it could make your problem a little messy if you do that. So let's write the first one. So we have V2 over R4. So again, KCL is all about the current entering and leaving a node. So we're taking a look at this problem right here. We're looking at this node is our analysis point. So that's where this equation is coming from. So we have, like I said, I always do leaving as positive. And it's up to you. You can do all entering, you can do all entering as positive and leaving as negative, or you can do as I do, leaving as positive, entering a node as negative. So we're just going to assign currents. So there are 3 possible currents for V2 because there's only 3 branches. We have the branch of current going this way. We have the branch of current going from through R3 this direction, and we got the current going that way. So the V2 over R4 is that branch. That is that current. The next one is, let's just take a look at this branch. This is this current right here. Is V2 minus V1 over R2. And then this current here is this one, which is V2 minus V3. Okay, just to slow this down a little bit, just so that if you're slightly confused, we write the KCL equation for one of the nodes. So we're going to start with this node here. We're going to start with V2. And that current, so we got possible 3 currents. There's only 3 possible ways current can enter or leave the node. And again, I'm using leaving as positive. So we start with this. We're going to call this I1, I2, and I3. Don't get this confused with node 1, 2, and 3. It's just arbitrary. Or Let me back this up just so that there is no confusion. We're going to call this I X, I, Y. Oh, I see they're using X, Y, and Z. Don't want to try to make this as we'll call it I N, I M, and I G. So IG plus IM plus IN must be equal to 0. That is the KCL. We have to maintain that. So IG is simply V2 over R4. The IM, which is this component, and we can do this in any order, is going to be V2 minus V3 over R3. And then the other one is we have V2 minus V1 over R2. And all that must be equal to 0. So if you have questions on this, please ask me to expand upon this in the live Q&A that we're going to do for this lecture, because I know this can get a little, since this is the first time you're doing this, you might get a little confusing. But just to highlight it once more, we're looking at this node is this equation, and we're looking at this part here is this current here. This part here is this one here. And then this part here is this current. All of them are leaving. And it's all equal to 0. Okay. So I'm going to go ahead and erase all of this. I'm going to scribble here. So, continuing on, let's look at this node here. So we have 3 nodes, and well, 4 technically with the reference node, but we have 3 nodes, and we're going to look at each one of these separately. So now we're going to write a set of equations for node 3. What do you think this is going to be for? We're at next. What do you think this is going to be? So let's just draw this out. So we have a current going this way. We have a current going this way, and there's also only 3 possible currents, all leaving. So just let's ponder for a moment. What do you think this is going to be? Well, what about this one? Let's first analyze this current here. What's that going to be? That's easy. It's V3 over R5. Okay. What about this current right here? Well, that one there is V3 minus V1 over R1. It's the current that is going this direction. And then this one here is V3 minus V2 over R3. So we have 3 currents. Then, of course, all that added together must be equal to 0. And that's exactly what happens. So now we have 2 equations, and we technically have one more equation here. We have a known. We have this node. Well, what about that one? What can we say about that? Well, that one's easy. We're given that. V1 is equal to Vs. So we technically have 2 unknowns and 2 equations. Technically, we have 3 values and 3 equations, but like I said, one of these nodes are known. V1 is equal to Vs, so that's now a known. And we have a system of equations, and the rules of system of equations, as long as you have the number of equations equal to the number of unknowns, you're in good shape. So we have 2 equations and 2 unknowns. We're ready to solve this problem. So this really becomes an algebra problem at this point. So I'm going to kind of step through this fairly quickly. At this point, the analysis part is completed. You now have a set of equations to process. Now it's just a process of solving the algebra. and this could be a little tedious. I mean, right now this one isn't too bad. It is really two unknowns with three values, V1, V2, and V3. V1 is known. You've got two equations. You're going to solve one in terms of the other, putting in the value for V1, using the resistance value. So the math is going to look a little messy because there's all these, R1, R2, R3, R4, and R5, and VS. So it's a lot of variables. Most of the problems you're going to have and the problems are going to be tested, the values actually are set, so you can actually reduce this as you go. So step 5 is just simply solving the set of linear equations. So here we solve V3 in terms of V1 and V2, again V1 being a known value. And we just combined all the terms. We have obviously have taken this equation and have simplified it a little bit. And we simplify it a little bit more, and we get everything, V3 in terms of, again, R2. What I did here is I just turned this 1 plus R3 over R4 plus R3 over R2 in terms, I just called it RY, just to kind of simplify the math. Broke things out, kind of combined everything, and simplify that. Called this 1 plus R5 plus 1 over R3 plus R1. I called it RX, just again to kind of make the math a little easier. So here we continue solving, and I'm using things in terms of the RX and RY. So just a lot of algebra. So by now you should be used to this in all of your classes. So just keep slogging on through. Now we got V2 in terms of the R's and V1, and V1 is known. At this point, you actually can compute V2 because V2 is now RX, R3, R2. So now once we know V2, because we were able to use the other equation and combine that and simplify everything, keep reducing. So in summary today, we did an introduction on nodal voltage analysis and this new method for actually having a system of equations that are developed in basically pulling apart a circuit and getting down to the point that we can actually put a voltage at every node and have a very set of create a set of equations that we can use to do circuit analysis, actually determine all the currents, determine the power and elements, etc. And this is just one of two different methods that this class shows for that. The following two lectures on nodal voltage analysis, the next lecture is going to cover method for solving a set of linear equations instead of going through all of the algebra method, just kind of going over this new matrix linear algebra method that you will actually learn more about in probably further studies in your engineering education here at Texas A&M. But we're just going to give you kind of an introduction to that so that you can actually leverage this mathematical method for solving these equations. And then the final set of lectures just is kind of bringing out more of showing examples of the problems for nodal voltage analysis and showing the method again. So if you have any questions, please just come to the live Q&As and we can go through things or come to the office hours. Thank you.